Welcome everyone, and I'm happy to see you again today. Last before we go into what we have today, let's make a recap of what we did last week. Last week we talked about classification of drawings and made us understood about machine drawing, walking drawing, part drawing. These were some of the things we did last week. Assembly drawing and all of them. So we also talked about application graphics and all the rest. Then the most important thing we talked about, I also told you about the standardization and the ISO, the British standard, and I knew I gave assignment, and not every one of us have turned in their assignment. This is not proper. Mr. Yomi, I have not started. I'm making a recap. So this is not proper. Please, this is engineering drawing. Let's try and practice it. Then we also talked about projections. We talked about projections, first angle projection, third angle projection, oblique, and these were all we talked about last week. So were all we talked about last weekend. We were able to establish some fact about it. We showed ourselves about it. But in order not to take our time, I will also show you the symbol of first angle projection and third angle projection. And I made us understand that in your quadrant, then the first is the first angle projection. So today, we're going to be talking about engineering curve. Today we'll be looking at engineering curve. That is what we'll be talking about today, engineering curve. Now you see some diagrams or drawings, they have different curves, they have different shapes. So what happens? So now let's quickly take this down. Designing certain objects requires shapes made out of curves which satisfy specific mathematical equations to meet the functional, artistic, and ergonomic requirements of the object. Designing certain objects required shapes made out of curves which satisfy specific mathematical equations to meet the functional, artistic, and ergonomic requirements of the object. So now here we'll be talking about the ellipse, the parabola, the hyperbola. We'll be talking about them, which you are seeing on the slide right now. Now under the ellipse, we'll be looking at concentric circles, rectangular methods, oblong methods, arc of circle method, then robust method, then basic locus method. Then for parabola, we'll be looking at something like rectangular method, method of tangent, that's triangular method, then basic locus. Then for hyperbola, we'll be talking about the rectangular hyperbola, then we talk about the coordinates given, the PV diagram equation given, etc. Now let's establish the fact that ellipse, parabola, and hyperbola are called conic sections. They are called conic sections. Ellipse, parabola, and hyperbola are called helix sections. And somebody might want to ask, why are they called helix sections? Now they are called helix sections. Sorry, they are called conic sections. Someone want to ask, why are they called conic sections? Good, thank you. They are called conic sections because the curves appear on the surface of a cone. Because the curves appear on the surface of the cone when it is cut by some typical cutting plane. So just like the diagrams you can see on the screen. So when you see them, when these are cut, they are all they are conic because when the curves appear in surface of a cone when it cut by a typical conic plane. So this is why we call them conic sections. Now remember I said ellipse, parabola, and hyperbola are called conic sections because these curves appear on the surface of a cone when it is cut by some typical curving plane. Now let's quickly look at some common definitions about this. There are the loci of points moving in a plane such that um, the ratio of k distance from a fixed point and a fixed line always remains constant. So let's look at these eccentricities, the eccentricities. Now, for to establish it, for ellipse, eccentricity is less than 1. The eccentricity for ellipse is less than 1. For parabola, the eccentricity, which is denoted by the cap lock E, is equal to 1. Then for hyperbola, the eccentricity is greater than 1. Is greater than 1. So now let's quickly move on so that we do some drawings today because you have to reproduce. And I want again in this class, please let's try and get A4 sheets always by our side. A4 sheet already titled and already designed with the border lines and the title block because we might be doing some drawings as time goes on. And I want you to be prepared. Next week we'll be having our first online test and it's going to be drawing. Get your A4 paper ready, get put the border lines and title it. After immediately you finish before the end of the course next week, before the end of our period, you snap it and forward it straight to my email. Then the hard copy, give it to your coordinator whenever school resumes because we're going to look into them. And don't forget to put your center name and the rest. Now, ellipse, it is a locus of a point moving in a plane such that the sum of k, the sum of k distances from two fixed points always remain constant. So now this is ellipse. I said ellipse is a locus of a point moving in a plane such that the sum of k distance from two fixed points always remains constant, and the sum this sum equals to the length of the major axis. The two fixed points are focus 1 and focus 2. The two fixed points are focused 1 and focused 2. You can see that on slide 5. It is a locus of a point moving in a plane such that the sum of its distance from two fixed points always remain constant. And this sum equals to the length of major axis. These two fixed points are focus 1 and focus 2. Focus 1 and focus 2. Now let's look at the loci points. The loci points of the loci points is the path taken by the point as it moves in space. The loci point is the path taken by the point as it moves in space. Now, for example, if a point moves on a plane in such a way that it keeps its distance constant from a fixed straight line, the locus of the point is a straight line parallel to and at a distance equal to the given distance. So these are the examples. So now conic sections. Conic sections. Let's quickly look at conic sections because I'm not going to be talking about definition today. I just want us to practice some things on our own. Conic sections. These are curves formed by the intersection of a plane with right circular cone. Right circular cone is a cone that has a circular base and the axis is inclined at angle 90 to the base and passes through the center of the base. It is a curve formed by the intersection of a plane with a right circular cone. Right circular is a cone that has a circular base and the axis is inclined at angle 90 to the base and passes through the center of the base. Now, conic sections are always smooth. More precisely, they never contain any inflection point. Conic sections are always smooth. They never contain any inflection points. It is important for many applications such as aerodynamics, civil engineering, mechanical engineering. So the conic section is important for um, aerodynamics, civil engineering, mechanical engineering uses. So it is important. So let's move to slide number 9, which also called a conic is defined as the curve traced by the points moving in a plane such that the ratio of its distance from a fixed point and a fixed line is always constant. Please, a conic is defined as the curve traced by the point moving in a plane such that the ratio of its distance from a fixed point and a fixed line is always constant. The fixed point is called the focus and the fixed line the directrix. The fixed point is called the focus and the fixed line the directrix. The ratio is called the eccentricity. The ratio is called the eccentricity. Eccentricity is equals distance of point from focus all over distance of point from directrix. I said again, electricity is equals distance of point from focus all over distance of point from directrix. Now, like I said before, for ellipse, the eccentricity is less than 1. For parabola, the eccentricity is equal to 1. And for hyperbola, the eccentricity is equal to is greater than 1. The electric eccentricity is greater than 1. So you can see that from the figure, the diagram that to your right about that. Now, an ellipse is defined as a curve. We can also define ellipse as a curve traced by a point moving in a plane such that the sum of its distance from two fixed points is always the same. Now, an ellipse is also or can also be defined as a curve traced by a point moving in the plane such that the sum of its distance from the two fixed points is always the same. So now this is the terminologies for the ellipse. So let's go to what we have for today. Let's go to for what we have for today. Now let's move on to slide 12. Let's move on to slide 12. Generating an ellipse, concentric circle method. Now let's look at slide 12. Now please let's pay attention. Now if you look at slide 12, please slide 12. If you look at the concentric circle method, we want to reproduce this diagram that is on my right. Please move to slide 12. Slide 12. We want to reproduce this diagram that is on the right of the slide. Thank you. No, slide 12, please. Now, if you look at, we are using concentric circle method here. Concentric circle method. So, how do we reproduce this? This is why I said every one of us get A4 sheet by your side, because we are going to be reproducing whatever we are seeing right now. So, if you can screenshot it, please screenshot it and do the practice on your own. Now, using generating an ellipse, that is concentric circle method, what do we do? Step one, Step 1, draw both axes as perpendicular bisector of each other and name their ends as shown. You name their ends A and B. Now, taking their intersection point as a center, where they meet is an intersection point. Taking it as the center, draw two concentric circles. Draw two concentric circles, considering both as respective diameters. Two concentric circles, considering both of them as respective diameters. Then step 3, divide both circles in 12 equal parts. Divide both circles in 12 equal parts. Divide both circles in 12 equal parts. So you divide both circles in 12 equal parts. Then step 4, from all points of outer circle, draw vertical lines. From all points of outer circle, you draw vertical lines. From all points of outer circles, you draw vertical lines. So these are, we want to be reproducing this just the same way it is here. So we will be reproducing it. So step 5, from all points, step 5, from all points of inner circle, draw horizontal lines to intersect those vertical lines. Draw horizontal lines from all points of the inner circle to intersect the vertical to intersect the horizontal lines, to intersect the vertical lines. You draw that to intersect the vertical lines. So point number 6, step 6, mark all intersection points properly as those are the points on ellipse. So you mark all intersection lines properly since they are the points on ellipse. So this we're going to be reproducing this. It will be shown on our screen now. We'll show it on our screen now on the slide. The slide will put it on our screen now. So let me say, go to slide 12. Slide 12. Now, the 7 point, step 7, thank you. Now, this is, you can see it on the slide. Please, if you can screenshot it, I'll be glad you do. Do screenshot it and practice with it. So, I want one of the assignments you're going to do for me is to produce what you are seeing on the screen. Produce it in your A4 sheet with the title block and the borderline set. So, because everything, produce this same figure. And step 7, I said, join all the points along with the ends of both axes in smooth possible curve. So you join all the points together. So this is concentric method. This is concentric method. This is concentric method. So the next one we'll be looking at here is another one using the unblocked triangular method. The unblocked triangular method. That is slide 13. The unblocked triangular method. So for this course, please, I will advise everyone, every slide, please screenshot them. You're going to practice as many as you want. I want us to be familiar with it. Now for the unblocked rectangular method, all we do is we draw a rectangle taking major and minor axes as the sides, just what you are seeing now. Then in the rectangular, draw both axes as perpendicular bisectors of each other. You draw them as perpendicular bisector of each other. Then now step 3, what you do now is for construction, select upper left part of the rectangle. The upper left of the rectangle, um, you select it. Then you divide vertical small side and horizontal long side onto same number of equal parts. So what you do, what I'm saying here, that you select upper left part of the rectangle, then you divide the vertical small side and horizontal long side into same number of equal parts. So you divide them into same number of equal parts. So if you see what I can see there, you can see I numbered them 1, 2, 3, 4. All of them are of equal parts, and that is what I am saying here. Then step 4, join all vertical points. That's 1, 2, 3, 4 to D. Join them to D. You can see my D at the top. That's the vertical, the D. You join all of them with a straight line to D. Join all of them. And all horizontal points 1, 2, 3, 4 at C, you join them to at C. If you check C, the base is C, so you join them to each line as you see. So I want you to reproduce what you are seeing on the screen. I want you to reproduce it, know it very well. And step 4, join. Okay, then step 5, extend C1 line up to D1 line. So you use a straight line, C1 line, you extend it to D1 line, then C2 line, just the same thing, and you get everything done the same way. Mark all these points properly and join all along with end A and D in smooth possible curve. In smooth possible curve. So now what we're saying here, after you join them, so you use a curve to put all the lines together. Wherever they intersect, wherever the lines C intersect with the line D, you mark it properly, then you use a curve to draw it so that they all align with each other and you'll be having an ellipse. This is the unblocked method. So please, I want us to try this. I want us to try it. I want us to try it. That is the assignment I'm giving. So please try, at least try as many as you can and snap it, send it to me. And next week we'll be having our first test on, or our test on engineering drawing. So be prepared. And as soon as we start the test, I'm not going to talk much. It's just the test we're going to do or whatever. Let's see what happens, but just be prepared of our test. Then the next one we're looking at again is parallelogram method. Parallelogram method. Parallelogram method, or what people say parallelogram method. So this is another method you see here. Now from what we did previously, you can do this. You can draw this with the same way steps we carried out in the previous one. All you just need to do is get the point, you divide them, then you join them wherever they intersect, mark the point and use a curve. Use your French curve. Please, I've told everyone, try and get the curves. Now for this class, you have to use a curve to join them so you have a perfect curve. Don't use broom. Don't use broom. It's not advisable. Get your French curve. French curve will give you all the curves that you want in in engineering drawing. Now let's look at the arc of circle method. Arc of circle method. So you can see that here again, the arc of circle method. So when you are about to do this, first thing you do is you draw both axes as usual. Draw them as usual. You name them, you name the end and intersecting points. So you just draw them just the same way we'll be following the steps. Then you name the ends. This is slide 15. So when you name them, then we carry on. Then taking a zero distance, take the distance a naught, a zero, or whatever you call it. Take the distance a zero. Then all you do is, that is, you take the distance a zero. And if you check slide 15, my a zero the is half of the major axis. Then from C, mark F and F on AB. From C, mark F and F on AB. That is from C, you mark F1 and F2 on AB. You mark them. Then taking F1, sorry, on line F1 to 0, take any distance, mark point 1, 2, 3, and 4. Now from F1 to 0, take any distance, you mark point 1, 2, 3, and 4. Now this is not you marking it. You can use your pair of compass or divider to mark it to make sure you get the accurate stuff. They may have the same distance. Now taking F1 center with distance A1 from the diagram, F1 with distance A1, then what do you do with that? Then draw an arc above AB. You draw an arc above AB. You draw an arc above AB. So you could see the arc. The curve on top is the arc AB. You draw an arc above AB. Now when you draw the arc above AB, now after you follow the steps you've seen now, you draw the arc above AB. So you draw the arc above AB and taking F2, as the center, taking F2 as the center now. When you take F2 as the center, what else do you do? With B and 1, with B1 distance, when you take F2 with B1 distance, then cut this arc, cut the arc, name the point P. You cut the arc and name the point P. Cut the arc and name the point P. So you could get it from there. You see it, and where we have our P1, P2, P3, P4. That is what we mean by that. Then 5, intersection point of the two arcs are point on the ellipse. The intersection point on the two arcs are points on the ellipse. Then step 6, repeat these steps with same center, taking now A2 and B2 distance for drawing arc, name the point P. So you take follow the same procedures and name it P. You can name it whatever you want to name it, but I named this P. So if you want to follow this, it doesn't matter. All you just need to do is follow it and let me know the steps you take. So I'll be able to measure it and see that okay, everything is well done. So in step 7, get all other points P, that is a P, P1, P2, etc. and join all points by smooth curve. To get an ellipse, use a French curve. So I've told you, use a French curve to get your ellipse. So, and that is that is the arc of circle method. There are different methods. So let's look at tangent and normal to ellipse at any point on it. Now, the if you look at the next slide, slide number 16, if you check the slide, you find out that we have some diagrams there, and like the bisector method when focus and directories are not known. When focus and directories are not known. So what you do in this case, the first thing you do is obtain the foci, the F1, on major axis with C. At the point P, TT is the required tangent. So, and when focus and directories are known, all you just do, this is when you now know the focus and the directories, then all you just do is follow the steps on the second diagram below it and you get it done. So let's move. Let's move. For the parabola, a parabola, slide 18. A parabola is a conic whose eccentricity is equal to 1, which I just said. It is an open end curve with a focus, a directrix, and an axis. So if you see what the terminology is, this is the parabola we have here. So please, can we move to slide 19? Slide 19. So I want you to produce this parabola. Slide 19. Thank you. Please, class, I want us to produce this parabola as part of our assignment. Produce this. The steps are all there. All you just need to do is you locate a center of the line perpendicular to AB. So produce similar thing and make sure you follow the steps to get it, and do it often and often so that when you see it in your exam, it will not be strange to you. Now, when generating a parabola, the slide 20, I also want you to do the slide 20 as a part of the assignment. I've given about 4 assignments now, so please let's try and do them. Follow the steps for focus directories or eccentricity method. So draw directories AB and axis CC. Mark F on C prime such that CF is 60 millimeters. Mark V at the midpoint of CF. So please, I want to slide 20, please slide 20. I want us to produce exactly this, what is you see on slide 20. Please, let's produce it. Slide 20. That's the next slide, please. Please, let's produce the diagram we see there and follow the steps So slide 20 is important. So I want to like many of us did not turn in our assignment last time. So, and please don't bother to submit that assignment again. Let's do this one. Now, generating a parabola, the tangent method. So you can see that on slide 23. See how it is being done on slide 23. Slide 23, you draw the base, the RS, which is equal 70 millimeters, through arrow and S. Draw the lines at 60 degree to the base, meeting at L. Then point 2, you divide RL and SL into the same number of equal parts, that is 6 numbers. The division as 1, 2, 3, 1, 2, 1 prime, 2 prime as shown on slide 23. Join 1 to 1 prime, join 2 to 2 prime, and so on. Now, for the first step is you draw a smooth curve starting from arrow and end at S and tangent to 1. So you do that on slide 23. So this is the tangent, tangent method, parabola tangent method. That is the parabola tangent method. So please let us look into that. And we also have the hyperbola. And I said hyperbola is defined as a curve traced by the point moving in a plane such that the difference between its distance from two fixed points is the same in the same plane is always the same. I said hyperbola is defined as a curve traced by points moving in a plane such that the difference between its distance from two fixed points in the same plane is always the same. The fixed point represented represents the foci or the foci, whichever you call it. Then again, hyperbolas exist in a pair. It is a it is an open-ended curve. Hyperbola is an open-ended curve. So hyperbola is an open-ended curve. So we could see the um, uh, uh, focus directories or eccentricity method for generating hyperbola. So I want to say thank you for listening to me. We do not have enough time, but please let's be prepared for next week, and we'll be doing our several classwork and assignment, and even we might do our test that next week. But if we could not do our test next week, we might decide to take it to upper week and do class assignment, class work. So I want to thank you again for listening to me. Please do well. I know we couldn't get everything, but just try and practice what you get and send it to me. I'll be glad to reply you. Thank you and God bless you. Do have a lovely day, and please stay safe till we meet next week. Thank you.